Hello, everyone. It's a great pleasure to be speaking to you about systematic reviews and meta-analyses. We have a difficult task, so I was asked to cover systematic reviews and meta-analysis in 20 minutes. So we'll see if we can achieve it. I have no disclosures to disclose. When you look carefully at the terminology of systematic reviews and meta-analysis, we realize that systematic stands for using a fixed and organized plan, so a systematic way. Meta stands for moving to a new higher level, and analysis stands for detailed examination. So systematic reviews is a structured plan to identify the literature, while meta-analysis is the statistical part to pull the studies together. Although some systematic reviews are combined with meta-analysis, many systematic reviews do not conduct meta-analysis, and many meta-analyses as well are conducted outside the context of systematic review. The statistical part of meta-analysis can be applied for randomized controlled trials, can be applied for observational studies, diagnostic accuracy studies, network meta-analyses, and even at an individual patient level, looking at individual patient data meta-analysis. The first step is to develop a protocol. The protocol needs to be done a priori before starting the study. You could register the protocol in Prospero if desired, which is a protocol registration website. It also can be published at supervised students and residents and junior colleagues, where we ended up publishing the protocol for systematic reviews. However, rarely you will get good feedback prior to publication, and the delay in publication as well is a major problem. This slide summarizes the process of developing a systematic review and a meta-analysis. Obviously, as with any research project, it starts with formulating a question, and the question needs to be structured in the PICO format. And the PICO stands for P for population, I for intervention, C for comparator, and O for outcome. For example, here we're interested in PPIs compared to H2 blockers in critically ill adults. The population will be critically ill adults, and then you have the interventions, but you also need to specify the outcomes, and the outcomes must be patient-important outcomes. So in this case, we're looking at both the potential benefits, like clinically important bleeding, and also the potential harms, like increasing risk of pneumonia or change in mortality or infections. In addition, you need to specify what kind of literature you're looking at. Are you looking at RCTs, or you're looking at observational studies? So in this case, we're looking at randomized controlled trials. Again, you have to specify if there is any language restriction. So are you looking at English studies or studies published in English language, or you're looking at all publications? The time frame, for our example, in PPIs were not existing before the 1980s, so it makes perfect sense to search from 1980 onward. And the last probably is publication status, whether we're looking at published or published and unpublished data as well. So these are the decisions that you need to make when you decide about the eligibility criteria. The second is to decide several hypotheses a priori to explain heterogeneity. And when we say heterogeneity, remember, we are including different studies and putting them in a meta-analysis to pull the results across those studies. So any differences in the results of those studies from each other could be explained by several things, by studies addressing different patients, or they're using different interventions, for example, higher dose versus lower dose, or different outcomes. And we expect that the effect, and I'm going to show you that in the next few slides, to be consistent across all the studies. After you decide about the question and methodologic criteria, you set some hypotheses to explain heterogeneity, then you start with a search strategy. And the search strategy is basically designing the tool or the approach how you would search the literature to identify relevant studies. And the goal is to include all relevant studies as possible. So critically ill patients, studies that examines PPIs versus H2 blockers, so all the PICO criteria, and all the other criteria that we specified, like looking for RCTs, all languages, etc. And then the search is going to look something like this. This is a RCT filter. So these are terminology that will be put into a search engine to help you identify randomized controlled trials. You combine them with the interventions, so search terms for PPIs, search terms for H2 blockers, and again, also plug it in with the population. And this way you end up with a comprehensive search strategy. So what should you do? You should search electronic databases. I think minimum of 3, midline, Embase, and central, but there are others as relevant, and you can educate yourself by looking at those resources. Some people will hand search key journals or search the reference list from relevant articles. They may contact lead authors, look at personal files, or even look at conferences and proceedings. The idea here is you try to identify all studies that are relevant to the PICO question that you're asking. Some tips to increase the efficiency of search strategy. It's better to involve a medical librarian. Remember that it's an iterative process, so it may start with something but end up with something a little different, so you tweak it till you get the final product. I think the most important in this slide that probably aiming for a sensitive search where you don't want to miss studies as opposed to a specific search which could run the risk of missing studies. So after conducting the search, the results of the search will be given to the reviewers. And the next step is title and abstract screening. There are several electronic platforms that can help. Things like Covidence, you can use other like Distiller or other softwares that are commercially available. At the beginning of the stage, you expect a lot of citations. This process will need to be done by 2 reviewers. So if I was the reviewer number 1, one of you will be reviewer number 2. We'll have to do the process separately and independent and in duplicate. After reviewing the title of an abstract and selecting studies, the next is to look at those studies more carefully and make sure they are eligible to be included. So what we call this step is full text review. So you'll get the PDF for those studies, and you will look at it and make sure that the study meets your eligibility criteria that you set. And again, this needs to be done by 2 independent reviewers. And the idea to achieve consensus, if there are disagreements, for example, I wanted to include a study, and one of you, the second reviewer, disagreed, then we may require an arbitration by a 3rd reviewer to make a decision. I don't have time to discuss kappa, but there is also a statistical measure to measure agreement between the 2 reviewers as well. You can look it up. This is what we call a Prisma flowchart. So at the top, we started with 1,215 articles. After removing duplicates, we ended up with 930 for titles and abstract screening. Out of those, the majority were completely irrelevant, 880 articles, which is expected. That's the typical finding that you see during the screening. And 45 articles or PDFs underwent full text review. We excluded 30 for several reasons. And eventually we included 15 studies with 1,720 patients. So this is a typical Prisma flowchart that you would see when or you would produce when you conduct systematic review. After identifying the study, the next step is to abstract the relevant data and assess risk of bias. And just a few words about bias is a systematic error or a deviation from the truth. It can occur in either direction, so it can bias the results to harm or benefit or no difference. And also, it can vary in magnitude, can result in huge difference or small difference. But sometimes, even though studies are poorly done, the results may remain unbiased. So remember, when you assess the risk of bias because it's difficult to prove its presence. For randomized controlled trials, the most famous tool is called the Cochrane Risk of Bias tool. And I don't have time to go through it, but it assesses several domains for each of the individual studies. And this is how things look like. So if you look at the figure on the right-hand side, and you see that studies are listed, and there are several domains that we assess the studies as for risk of bias. And for those assessed as low risk of bias, they have to have low risk in all domains. So here, for example, we have 3 studies. If any of the studies have high risk of bias in any of the categories, they will be classified as high risk of bias. And for those who have unclear risk of bias, they will be classified as unclear risk of bias. So after abstracting the data from relevant studies and assessing risk of bias, the last step is to conduct data synthesis. So how would you summarize the results? Which measure of effect is what we call the effect measure. So there are relative effects, we call relative risks or risk ratios, odds ratios, or hazard ratios. And there are absolute effects like mean difference and standardized mean difference. And just to give you an overview of what meta-analysis is, you will have several studies, A, B, C, and D in this scenario. Each will have their own data and outcomes. And at the study level, each study will have its own results, so what we call effect measure. Pooling all of these effect measures to produce a common or an average effect measure, obviously it's not a mean score or anything like that. You have to transform it to log scale, and then it transform it back. So it's a complicated process, but at the end, you will have an effect measure across all the studies. And this is what we call a forest plot. And for binary outcomes, and binary outcomes are outcomes that are either present or absent, like mortality, either the patient died or survived, like having a heart attack, either they had a heart attack or they didn't. So these are called binary outcomes. For those, we can use risk ratio or relative risk to present the results. And as you see, the small squares represent the individual studies, and the diamond represent the pooled estimate that I showed you in the previous slide. And the weight, it just describes the weight of how much of the information is produced by the study. I'll skip the slide, and then the next slide here, it's important also to notice that there are the chi-square and like a p-value and an I-square for heterogeneity, which I'm going to explain later on. Just keep this in mind. You also could summarize the results for binary outcomes by using odds ratio. The difference, and this is the same set of results, but you can see some differences when I compare relative risk to odds ratio. So they don't produce exactly the same results all the time. For continuous outcomes like ICU length of stay, blood pressure, things like that, we typically use mean difference to summarize the treatment effect. And as you can see, because it's a difference and it's not a relative effect, you can see for reduction, you'll have the minus sign, and for positive results, you won't see the minus sign. When we are using different scales, in this case, the effect of physiotherapy, for example, and some patients, they use different scales to measure the effect. And you can't really combine them because they're using different units. You have to transform them to something called standardized mean difference. So just know that this also can exist when you have different ways of measuring the outcome when it's continuous. Sometimes you may be faced by an outcome that's an ordinal variable, which is an ordinal scale or categorical scale that, for example, here modified ranking scale has 6 categories, so it's not a continuous outcome. And also it's not a binary outcome, and which what we call ordinal variable. And there are many ways to do it, but one of the ways is to produce something called proportional odds ratio. Just know that there is statistical methods to do it, and you can always consult a statistician if you get faced with this scenario. I'm going to touch very briefly, because we don't have time to discuss in detail, about random and fixed effect model. On the left-hand side is the fixed effect model, and the random effect is on the right-hand side. And the only major difference that the fixed effect assumes one common truth, and the difference between the effect of the studies and this truth. However, in the random effect, it takes into account between study as well difference. This is why it produces a wider confidence interval, so less precise result and more conservative. Typically, we like to use random effect almost always, except certain scenarios when we have less than 3 studies, or when there is a large, well-done study that we want to give more weight, so we can use fixed effect model. Also, I need you to know that there are several methods and to other than random effect and fixed effect. And for the same data set, you can see fixed effect model results in the smaller diamond, so narrow confidence interval. There are other more conservative approaches that are out there. So there are typical random effect model, but also there are other approaches that are available that are more conservative. Next, we'll just spend a few minutes on heterogeneity. And I'm just going to show you that, for example, these studies, they're all telling us the same thing, and the results are consistent. But look at the left-hand side. Although the blue diamond is a similar result to the blue diamond on the right side, when you look at the individual studies, some studies are showing clear benefit and others showing clear harm, yet they resulted in the same estimate. And this is what we call heterogeneity, which means some studies are telling us different results than others, even though the pooled estimate resulted in similar results. There are different ways to measure heterogeneity. There is the chi-square test, if you look at the bottom of the figure, that produces a p-value. So if a p-value is less than 0.01, it's significant. In this case, it's not, so there is no heterogeneity detected. However, in this scenario, the p-value is less than 0.001, suggesting that there is statistical heterogeneity. There is also what we call the I-square test, which quantifies heterogeneity that is not explained by chance, and it ranges anywhere between 0 and 100. The higher the number, the worse the heterogeneity. So for the first scenario here, remember that I showed you the p-value was not significant, and the I-square is 0, indicating no heterogeneity between studies. However, in the second scenario, the I-square is almost 90%, which means that, apologize, let me go back, which means that 90% of the difference that you see between these studies is not explained by chance, which indicates a huge heterogeneity. So whenever you see heterogeneity, remember when I told you you propose hypothesis a priori for subgroup analysis, you have to look for explanations. Look if there is differences between patient populations, so younger versus older, for example, or the differences between studies because studies use high dose or low dose, or because of risk of bias, for example, high risk of bias versus low risk of bias. Another thing we should talk about is called publication bias. So small negative studies in the past, nobody wants to publish them, and they produce important missing studies. And sometimes industry, they conduct even large studies, but they don't publish them because they are negative. The way to test for publication bias is to look at the funnel plot, which I'm going to show you in the next slide. So in the y-axis is the measure of the study size. As you go up, the bigger studies in the top, and the smaller studies are in the bottom. And at the bottom of the figure is the effect size. And as you can see, there is some missing small negative studies. So on the right-hand side is the negative studies, and the left side are studies that are positive. So small negative studies are probably missing, and you can only use funnel plot when you have 10 or more studies. There are several causes of funnel plot asymmetry. You just need to know that publication bias is one of them, but there are several others as well. I think this is the last slide, and I apologize for the long presentation and for rushing through several information. This is meant to be an introduction for systematic reviews. So if you require more reading, there is an outstanding online available source, Cochrane Handbook for Systematic Reviews, and also the user's guide for the medical literature as well, an outstanding source as well for systematic reviews. I apologize for not being here today, but if you have any further questions or concerns, please feel free to reach out to me by email or on social media. Thank you.